All right, so like I said, this is going to be the last chapter that we'll be covering. So again, the third exam is just going to be on chapter 19, which is, you know, a good bit of material and different kinds of reactions. But again, right, if you follow the theme, okay, getting that alpha carbon, right, deprotonated by the base, right, creating the nucleophile, and then figuring out, right, what's going to get attacked. That's really, again, right, the key to chapter 19. So once you can kind of, you know, get that theme in your head, hopefully, okay, that's going to make the material in chapter 19 a lot easier to digest. But it is a good bit, and so here's the answer key. We're going to go over some of these on Wednesday. So Wednesday is a problem-solving day, so we'll do some of these problems. But you certainly are welcome to the answer key if you want to work ahead, or, you know, if we don't get through all your answers on Wednesday. And then remember, a week from today, we'll do the practice test as a review, and then the exam will be that following Wednesday. Okay, and so again, chapters 19 and then 22, which we'll go over today. Okay. And we do have a research club presentation today, and I did email the details there, but it is at 12:15, and I believe it's downstairs in Bradley, 121.
In Bradley today.
Everything is in Bradley today. Yeah, they even power washed the outside of the building to make it look like a nice backdrop. I mean, they're going all out. I don't know what this is, but I'm like,
maybe Trump is coming.
I want something to be.
Did that scare you? Like, I actually like drove over, like, these guys like white suits, and I was like, is it chemicals still there?
Yeah, like some decontamination unit. No, they were just power washing. We get emails about that stuff, but I guess students don't know what's going on.
I kind of drove over, see these guys walking around, so
just power washing. All right, so chapter 22 is reactions of benzene. So as I mentioned, chapter 21, there's some stuff kind of embedded at the beginning, like the naming and the structure and things like that. So if you do have, you know, questions on those portions, you might have to go to chapter 21 in order to see that if you're following along in the book. But for the most part, this is 22, and I'm not really going to ask any questions from chapter 21 on the exam. So we're just going to really focus on the reactions of benzene on the exam. But I think, you know, to kind of talk about the reactions, we have to understand a little bit about the structure and, of course, the naming system here for the benzene. And so usually, so we'll start with the monosubstituted, and that's usually the most common form of the benzene. And of course, benzene, right, is the 6-membered ring with the 3 double bonds that are conjugated. So I know we've already seen benzene a good bit in this course, but we haven't really done anything on reactions of benzene. So that's what the theme for this chapter is going to be. But of course, you can have substitutions to the benzene ring. So for instance, an ethyl, right, a methyl, right? So this is isopropyl. Does that make sense? So a vinyl. Okay, so you can have lots of different substitutions that are carbon-based. Okay, you can also have different functional groups attached to the benzene ring. And so these are just some examples. And of course, right, benzene is the parent name, and then whatever is attached is named as a substituent. So ethylbenzene. This is methylbenzene, but toluene is a common name that IUPAC accepts. So like when I buy methylbenzene, the bottle says toluene. But you can always name it, right, based on that. This is isopropylbenzene, right, but it's also cumene. Okay, and styrene, right, is vinyl benzene. Why am I not numbering? 1 ethyl, 1 methyl, 1? Because it's the only thing attached. Okay, so if you only have one thing, you don't have to number. Does that make sense? So the functional groups, some of them get completely different names. So for instance, when you add an alcohol, okay, it becomes phenol, right? So phenol is the substituent name of a benzene coming off of a chain. With the OL is phenol. With the nitrogen is aniline. Okay, and this is with the aldehyde, benzaldehyde. With the acid, right, carboxylic acid, benzoic acid. And then this is the ether, which is anisole. So again, some common names that IUPAC, you know, accepts as part of their naming system. Okay, so some of these you just kind of have to memorize, unfortunately. But if it's a methyl, like a carbon chain, you can always use the IUPAC substituent names for that. But like phenol, unfortunately, you just got to kind of memorize that one. Yes.
So when we're naming, is it okay with you if we just use methylbenzene?
Yeah, that's totally
Okay.
fine.
But on AL, you have to do that.
On AL, you just have to make sure, like you read, if they say IUPAC, you know, then you have to do it. But toluene, like I said, that's actually the common name. So if you do methylbenzene, that is IUPAC. So, but I don't think, because I only assigned chapter 22, I don't think there'll be any naming on this homework. And I won't have these as names on the exam either. So, and then there's difference between what's attached. So when the benzene here is directly attached to the chain, that's a phenol. Right, we've done that before. If there's an extra carbon chain, so it's really toluene attached, right? That's called benzyl. So phenol and benzyl. See the difference? There's a carbon here. This is directly attached. This is, right, one carbon in between. And it's abbreviated, right, pH for phenol, right? So this coming off of an R group, right? And this is BZ. Does that make sense? Okay, so you might see that abbreviation, so you know, just add a carbon in between, right? That's really the difference between the two. And so you just have some examples here. Okay, so as a substituent, right, because we know the chain has to include the double bond O. So this is the chain, right? Okay, and so the phenol is a substituent coming off of the first carbon. So it's one phenol, right, one pentanone, right, where the ketone is. All right, and then here, right, this is phenol, but with the methoxy coming off, right? But again, the main chain is 1, 2, 3, 4, right? Does that make sense? So this is going to be 2-butanone, right, where the ketone is. So 4 is the position where this big old thing is coming off of. So that's why it's 4 parentheses, right? What's that 3 about? It's where the methoxy is, right? In comparison, this would be 1, 2, 3, right? 3-methoxyphenyl 2-butanone. And then this one is Z, right? Because this big thing and this is the bigger thing on the other side. So these are on the same side. They're Z, right? The main chain, though, is 1, 2, 3, 4, right? It's 2-butene. So Z, 2-phenyl, 2-butene. So just some examples here. Yeah, so long. Seems like a lifetime ago. And something else about benzene that you might see is these non-numerical. So when you have di-substituted groups, so not just one thing coming off, but two things coming off of the benzene ring, you actually can use these non-numerical representations. So ortho is a 1-2, meta is a 1-3, and para is a 1-4. Okay, so if you look at something like this, right? 1, 2, 3, 4, right? So methyl is at 1, right? Bromo is at 4, or vice versa. This is a 1-4, so we use para as a non-numerical locator. So para-bromotoluene. But of course, you can call this, right, 4-bromotoluene also, right? Using the numerical if you prefer. This is a 1-3, right? 1, 2, 3. This is aniline. Right, so it would be 3-chloroaniline, but because it's a 1-3, you can call it meta-chloroaniline. Does that make sense? And this is a 1-2, right, so you can call this ortho-nitrobenzoic acid. All right, and it's important to know these because later on, these help us determine where the reaction is going to happen. I think you've already had a lab with meta-directors. Do you remember something like this in the lab? When you made the sulfonation reaction, I think? Or, sorry, nitration reaction with the two different acids. And you made, right, this product, and the product was meta. So you do want to pay attention to these, okay? Even though, again, I don't think naming is not going to be, okay, a big deal, but you want to know what ortho means and what meta means and what para means, because in a minute, okay, at the end, we're going to need to know those positions. Does everybody understand the non-numerical?
Just memorize them.
Just memorize them. Yes. Okay, so So what about when neither of the groups has a special name, like phenol, aniline, right, benzoic acid, whatnot? Then again, you can still use the orthopara, but you want to make sure that you use alphabetical order. So this is chloral, this is ethyl, right? C before E in the alphabet. And so you would want to give the chloral number 1 and the ethyl number 4, right? So in the numbering system here. So this would be 1 chloral, 4 ethyl benzene. But of course, it's also para, right? A 1,4 relationship there. So here, B before N, right? Bromo versus nitro. Does that make sense how this goes? But again, it's ortho, right? So ortho, bromo, nitro, benzene. Okay, and then these are 2 of the same, right? So it doesn't matter which one is 1, which one is 3. But again, you can use meta and use the di to say you have 2 dinitrobenzene. So just some things here. And then, of course, you can have a number of different substituents. So these are poly-substituted. So mono is 1, di is 2, poly is more than 2. And so in this case, you don't have to try to use the alphabetical order. It gets too difficult. Your goal is really to make sure that you get the lowest set of numbers to all the substituents. Okay, so in this case, chloro should be 1, right? Because C comes before M, comes before N, right? But you don't have to do that because you have so many substituents, it's going to be hard to achieve a low number, okay, following the alphabetical order. So it's better to just say 1, 2, and 4, right, than if this was 1, 2, 3, 4, and 5. Does that make sense? So those would be bigger numbers. And so these are just some examples of them. So, and again. And then phenol, so the benzene with the OH, they do have a number of substitutions, and the one I wanted, methyl, hopefully makes sense here. And of course, cresol is another common name. But the diol, so you know, remember if you have 2, you don't want to use phenol, right? You want to go back to benzene and then say that you have 2 alcohols, right? So benzene diol, does that make sense? So you don't use phenol and a hydroxy as a substituent or something like that. So I just want to point that out. Same thing here, right? 1,3 benzene diol 1,4, right? And you can see they each have its own name. So, you know, those are common names, which IUPAC doesn't recognize these. So you would want to do the diol. Does everybody see that difference?
This would be like para, like diol at the end, or would you?
Yeah, with these, you wouldn't want to use the para, the orthometapara. You would want to use, because of the diol, you want to convert it all back to the IUPAC. Good question. Yeah, so you know what you say, like, can we say orthobenzene diol? You really don't see that. Like, you use the IUPAC, you know, numbering system for these. So this is really, you know, an exception. And here are some commonly used. So phenols are usually used as antiseptic, disinfectant. So if you look at Lysol, for instance, you'll see a number of phenols are used as active ingredients for that. Also mouthwash, like you'll see phenols in like mouthwash as well. And so these are just some examples, and then these 2. And then the last one is actually the main component in poison ivy. So I don't know if anybody's ever experienced that. You know, it causes the itching. Like, it's a plant, and if you go out and you don't know what you're touching, you'll touch the leaf, and all of a sudden you are all itchy. So the component is also, right, a diol.
It's really cool seeing the oil. When I was in Girl Scouts, we had a sign where we put on gloves and we take poison ivy and we put them in plastic bags.
Yeah.
You just hung them upside down and you can see the poison, like
The oil coming off, yeah. Because that's really what it is. It's the oil that comes off of the leaves, but it tends to cause an allergic reaction, which is really unpleasant if you've ever had it before. So it's very unpleasant. I've had it before as well on my legs, and it was awful. So those are our naming. So now to start reactions. So the first reaction I want to talk about is acidity of phenol. So because phenol has an alcohol, right, so that hydrogen could potentially be removed. And the reason this is acidic and other alcohols are not are because the double bonds, right, the conjugated system of the benzene allows the anion to disperse the negative charge on the oxygen, making the pKa go down. And so most alcohols are neutral, okay, but phenol is considered a weak acid. And so if you put phenol in water, you do see, right, that acid, the hydrogen, right, is donated to the water, and you form the hydronium ion, which is a measure of, right, having an acid in water. So you can see that the pKa is 9.95, so about 10. So that's a weak acid. Right? But most alcohols, like here ethanol, when you put it in water, right, that pKa is 15, 16. That's not going to happen. Okay? So phenols, though, will produce the acid reaction. Okay? And the Y is because of the conjugation, right? That the double bonds here are going to allow, right, for a number of resonance structures which are going to alleviate the negative charge on the oxygen. There's nothing that we can do when you have, right, methyl groups like ethanol. There's no, right, dispersing that charge. So that's why you see that pKa difference. And so what we usually see is different, right, di-substituted, so the phenols with an additional substituent, and if that substituent is electron withdrawing, like chlorine, right? Chlorine is electronegative, it likes electrons, so it's considered electron withdrawing. Notice that the pKa, right, goes down from the original phenol 9.95, about 10. Okay, but if you put something like methyl, which is considered electron donating, it is not electronegative, so it's not going to be interested in pulling the electrons away from the benzene ring, then the pKa, right, doesn't get affected. Does that make sense? So you can use, so what would be even better than chlorine? What should I add over there? Fluorine, right? Fluorine would be great if you want to lower the pKa of a phenol. Okay, so alkyl groups, though, okay, they don't really do much. They're electron withdrawing. So, but it's going to, again, be something we're going to discuss with these directors in just a minute, meta, ortho, para. Now, Nitro Group, right, I don't know if I drew it up here before or if you had to draw it on out, but it is an ion, right? You have, right, something like this, right? And it is neutral because you have a positive and a negative charge, so it's what we call a zitter ion, okay? But it is electron withdrawing, right? Both the nitrogen and the oxygens are electronegative, so you have an effect, right? Pretty big effect on the pKa. So, yes, ma'am.
How come depending on where the nitrogen is, the pKa goes down?
Yes, because the position matters. So when you're too close over here, you don't even see an example because what's going to happen? You're going to have, right, they're going to be too close together and there's going to be a repulsion. Okay, so really you want to be para is the best position. Because yes, you get the electron withdrawing effect, okay, but the distance matters because you don't want to be too close and provide a repulsion. Yeah.
But that's with nitro groups.
That's with the nitro group.
Because with the
Yeah.
chlorine, I see it's better in the.
Yeah, because the chlorine is going to be smaller. Like the nitro group is a bigger group, so it's going to require a bit more distance. But it has to do with not clashing the OH with the electro withdrawing group. So this is called inductive effect. And of course, there's also resonance effect, which we'll see again towards the end of the chapter, because the way the electrons are going to flow, right, if you provide more ways for it to flow at the para, that's going to be more stable. So that's something else we're going to investigate in a little bit. So having those double bonds, right, those conjugated systems, the resonance effect is big too. Okay? Now that's, again, those kinds of things are from chapter 21. But again, not much of that is going to be on the exam. I'm not going to have benzene naming on the exam, things like that. But you do have to know what an ortho is, a meta is, a para is, because it's going to come up in the reactions.
They
You
do
keep
have
that in mind.
21 questions and bonus questions?
No. So no chapter 21. I just feel like without a little bit of background, it's hard to have the rest of the discussion. So that's why I put it in. I used to do chapter 21, but we kind of run out of time. So not this year, I guess. We could have had class on Wednesday and I could have gone on.
It's okay though.
Hopefully we got caught up on our homework. All right, so now to the reactions, and this is again what we're going to focus on for the exam. So these reactions are substitution reactions, okay? So So what you're substituting is a hydrogen. So this hydrogen right here is going to be substituted by a number of different things, including halogens. So this is called the halogenation reaction. So you can see that the H, right, and one of the Cl's, right, they are going to become HCl, and the other Cl comes in and substitutes where the hydrogen used to be. Okay, and we'll see how the mechanism works here. All right, but it is a substitution reaction. So same thing here with the nitration. So you did this one in lab, so remember that you combine the, nitric, thank you. Appreciate it. Okay, nitric acid and sulfuric acid together, and we kept the temperature low. Remember that reaction? So you did this one in lab, and what you did was take this hydrogen, okay, and again, you're going to replace it by, right, the nitro group, and of course, HHO, right, is water. That's what's left over, right? This hydrogen plus this hydrogen and one of your oxygens. That makes sense? Because then the NO2 is what gets substituted. And again, we'll look at the mechanism behind all these. You can also do sulfonation, and that's, I think you didn't do this one because I know Cheyenne is allergic to the sulfa drugs, but we usually do this one as well. But you're adding sulfur, right? So you're adding, a sulfonic acid group. So again, SO3H. Okay. You can also do an alkylation reaction where the R group replaces. So again, you use an alkyl halide to do this reaction. And then you can do the acylation. And remember, that has the carbonyl attached to the R group. And again, that replaces the hydrogen. Okay. So a number of different reactions for benzene. So what kind of substitution are we doing here? So we've already talked about some, right, substitution reactions like nucleophilic substitutions. These are electrophilic. Okay, so these are electrophilic, and they're also specific to benzene. So they're electrophilic aromatic substitution, or EAS for short. So you might see that on OWL. Okay, they like to kind of put that in. EAS is talking about, again, it's an electrophilic aromatic substitution. So what's going to happen here? This is where the hydrogen atom is going to be replaced by something, and that something is not going to be a nucleophile, but an electrophile. Does that make sense? So this is not a nucleophilic, but an electrophilic substitution. Okay? So we're going to first then, how do we generate these electrophiles, right? We talked a lot about how do we know what a nucleophile is, right, or what the nucleophile is. So now we need to investigate how do we get these electrophiles, because this reaction needs them, right? And then how is the mechanism, right, to replace that hydrogen achieved? Okay, because do you think that hydrogen really wants to leave?
No, it's
Not really, right? And so we need to make sure that we have the right conditions for this reaction to happen. All right, so this is the general mechanism for an EAS. Okay, so the first thing that you have to have is the electrophile. So we're going to discuss how we form it in just a minute. Okay, but it's going to be the electrons of one of the double bonds of your benzene ring are going to come and react with the electrophile. Okay, so the electrophile is going to be attached to the ring, but the ring is going to have a cation, so it's not happy, right? It wants to go back to being a benzene, and because this is so unfavorable, it's going to be the driving force to get that double bond back. That's what's going to drive taking the hydrogen out, right? Because the benzene ring wants the electrons back to make it a double bond again. Right, so it's going to allow for the hydrogen to come off as a proton. Does that make sense? So when it does, you now have the electrophile substitution. So again, now comes the question here. So this will not happen if you don't have an electrophile. So how do we get it? Okay. So first and foremost, what is an electrophile? By definition, an electrophile is what? Something that wants electrons, right? It wants electrons. It needs them. That's why it has a positive charge, right? Because it is missing a pair of electrons. Okay, so that's first and foremost, right? Understanding what's going on I think requires knowing the definition, but now how do we make that? So I'm starting with something that is neutral, right? A chlorine, Cl2, is neutral. So how do I make it positively charged? I usually see it as negatively charged, right? As the chloride ion, like a nucleophile type reaction. So how do I make it go, right, and become an electrophile? Well, I need a catalyst. And so you'll see that all of these reactions require a catalyst. And so this one is ferric chloride. So, right, the iron with the 3 chlorines attached. And what's going to happen is one of the electrons is going to react with the iron. Okay, so now you're going to have this complex here where the positive charge is now on the chlorine. Because would you agree the chlorine, right, gave away its electrons, right, for sharing with the iron. Okay, and iron is going to then, right, keep the negative charge because it gained the pair of electrons. Does that make sense? So now the chlorine, would you agree, is lacking a pair of electrons. And it wants to get it back, right? And who is it going to go and get it back from? The benzene ring. Does that make sense? So by combining, right, chlorine with the ferric chloride, I now have, right, my electrophile. Does that make sense? Yeah. Okay, and where's this one going to go? Right, one of these is gone. I only have one there. Or I'm sorry, no, this one is just a little bit the way to look at it, because eventually this one is going to go with whom? One of these with the H, right, to form HCl. Okay. The important part now is that we generated the positive charge on the chlorine, right? It's going to get the electrons from the benzene, right, forming that intermediate. But again, that intermediate is really unhappy with that charge there, right? Okay, and so it's going to go get that charge from the hydrogen bond. Does that make sense? Okay, and so that's what you see here. So again, now, right, this one, right, this chlorine is going to come and pick up the hydrogen, and the electrons are going to go back to form the double bond, and that's how you end up with the HCl. And of course, the catalyst, right, has to be reformed. So you get the ferric chloride again. Does that make sense? How this works, how to form. So you need a catalyst. And notice that the catalyst, the relationship here with the catalyst is an acid base, but it's Lewis acid-Lewis base, right? Remember that that's based on electron transfer, not proton transfer. Okay, so the chlorine is the base that's going to donate the proton, right? And the catalyst is the acid, which is going to accept. So just keep that in mind. It's, again, another definition. If you understand the definition, it might just help you see, you know, what's going on. And so this is the energy diagram for this reaction. So again, now it's not chlorine but bromine, okay, but it's halogenation still. So the benzene ring, right, with the bromine, and you can see that again, you're going to form that intermediate. So of course, this is a big step here, big energy step. So that's going to be the rate determining step, okay, getting that first, right, interaction, breaking the double bond and picking up the electrophile. Now notice, what if we, right, wanted to get 2, right, di-substituting, because I do have 2, would you agree? I have 2 bromines, or 2, right, Br2, so I could do 2 substitutions, but it's very unfavorable. See the difference in energy, right? Finishing it off by, right, bringing back the double bond is way more favorable than breaking the double bond altogether. So these don't undergo addition reactions, right? Right? Remember that benzenes don't react like other alkenes. Even though they have double bonds, they don't behave like other alkenes. So it's very unfavorable to do the di-substitution. So it's always a mono substitution. Do you understand what I'm getting at here? You're not going to break the double bond like we've seen with alkanes and add 2 bromines, right? We're going to do this, regenerate the double bond.
You take that extra step.
So yeah, you don't want to lose that conjugation on the benzene ring. So that's something to consider. All right, so let's look at some other electrophiles. How do we generate the electrophile for the nitration reaction? So the electrophile, right, is going to be NO2+, Okay, and again, and we did this in lab, and you again might not have been, we didn't cover it in class, so you might not have been aware of this, but this is what you are doing by mixing the two acids together, is to form the electrophile. So you can see here that there's, again, right, those electrons come, sulfuric acid picks up the hydrogen, right, so it's acting as the acid catalyst. Okay, and what it leaves you with is that positive, right, electrophile. So the conjugated acid there, the nitric acid. Nitrogen, I gotta think nitrogen. So that, right, step 2 is then losing the water to give you the nitronium, the NO2 plus. Okay, so this is forming, right, the electrophile. And then the electrophile can come in, and again, it really doesn't want to be in that form, right, as an electrophile. It's going to look for electrons, and it's going to find it in the benzene double bond. Does that make sense? And then again, the benzene, right, doesn't like having that positive charge, so it's going to, right, get it back. And water comes back, picks up the hydrogen, okay, and then again, it reforms the double bond. Does that make sense? The nitration step there. And then the product of the nitration, that nitro group, remember, it can be reduced to an amino group. So if you use, right, this is catalytic reduction, the hydrogen with nickel, right, so we've done that reduction step many a times before. And you can see it does not affect the carboxylic acid, right? You need another reagent, the lithium aluminum tetrahydride, so that stays the same, but you see that the nitro group becomes an amino group, so you can do that. So sulfonation, what's that like? So again, right, you're going to convert, right, the sulfonic acid here, or I'm sorry, you're going to make the sulfonic acid by again combining, okay, your sulfur trioxide with sulfuric acid. So then the Fidelskraft, again, you're going to be using now R group as your electrophile. Does that make sense? So how is that going to happen? This is probably the easiest to imagine, right? Because we know the chlorine will be happy to take the electrons, right, leaving the R as a positive. So this is a little bit more, I think, intuitive here. But again, it requires, right, the Lewis acid as your catalyst. Okay, so you can see it here again. If you think about it, right, you're going to be able to remove, well, that's what you're trying to do, remove the chlorine, right? And so you're going to combine it with the catalyst, and then it's going to leave the R group as a cation. And again, that cation doesn't want to be a cation, so it's going to pick up the double bond of the benzene ring. And then here, the chlorine is going to act, right, to get the hydrogen so that the double bond is reformed. And of course, you get HCl. Right, so the Fidelskraft. Alkylation. Now, there are two limitations to this reaction. Okay, so the carbocation rearrangement is going to be common. So you want to consider this when you are forming a carbocation, right? So if this is going to be the carbocation, if there's a better position, right? This is primary, this is tertiary, would you agree? Where's the reaction going to happen? Tertiary. At the tertiary, right? So you see that the product really is here, right? So you want to make sure you, right, keep rearrangement in mind. All right, so you show this in the bottom here. Okay, so you see the methyl transfer, right, the shift there to make the carbocation at the tertiary. Okay, and then the second thing is that alkylation fails if one or more of your substituents here, so if you have a mono-substituted or a di-substituted benzene, if that substitution is an electron withdrawing group, there is no reaction. So if this is a chlorine, if this is a bromine, if this is a nitro, if this is anything that's going to take away electrons from the benzene ring, you're going to get no reaction. So here's the groups that you want to be concerned with at that Y position. Huh?
Oh, you said so that's the Y position.
Yes, so see that if the substitution is an electron withdrawing group, right? So like you said, okay, nitro, fluorine, chlorine, right? Oxygens of all sorts, okay? Anything that's going to want electrons for themselves. And why would that be? Because what am I going to have to use but one of these double bonds? If this double bond is tied up with the electron withdrawing group, there's not going to be the double bond that I need. So you got to be careful when you're reacting a substituted benzene. Okay? So those are two things you want to consider. So then next is the acylation. So again, it's a very similar mechanism, but instead of just transferring a bunch of carbons, you are transferring a bunch of carbons with a carbonyl attached, right? That's the difference between an alkyl and an acyl. So the double bond O, carbon double bond O. But again, you have your catalyst, okay, to form your electrophile, and then your R group is what's transferred, right, or substituted. Okay. And you can do a cyclic type too, right? Because again, if you look here, right, this is going to be the Cl that's going to interact with your catalyst. So eventually you can form a bond here to close the system, right, using this mechanism. So this is the Friedel-Crafts acylation. And again, how do we form the electrophile, right? The acylium ion. Again, it's the chlorine interacting with the catalyst, aluminum chloride. Okay, again, it's a Lewis acid, Lewis base type reaction. And then that allows, right, for the transfer of those electrons, leaving your positive charge on your carbonyl carbon. Okay. So that's the E, right, the electrophile that you need. And again, it's going to go get the double bond, right, to get those electrons, and it's going to form the substitution product that way. Does that make sense? So again, right, same thing over and over again, but what you have to realize is what is the electrophile, right? What's the thing that you're going to be substituting the hydrogen with? Does that make sense? Any questions?
So for this propene, since it's going to prefer the secondary carbon as opposed to the...
Well, this is giving you some other things that might happen. So for instance, if you have an alkene, what's going to happen is you can treat it with an acid, so sulfuric, phosphoric acid here. And what's going to happen is you're actually going to form here with the double bond, right? An electrophile. Okay, and so again, right, the electrophile then is going to be here, right? And that's where you're making the reaction. So this is just, again, showing you you're going to use one of these acids to transform this into an electrophile. And a double bond does that, right? Because when you open this double bond, one of the carbons is usually left as a carbocation. We, again, saw that many a times in chapter 6, right? Carbocations are formed when you do those addition type reactions. So it's a similar situation, but the hydrogen is going to be added to the least substituted, right? Leaving the carbocation at the secondary position. So that's why you get the product here and not here, right? Does that make sense? Okay. You can also treat the alkene with a Lewis acid. So again, the catalyst we've been doing, aluminum chloride is one of them. So you can also treat your alkene with that. And again, you're going to form one of them as a carbocation, and then you're going to have the reaction with the benzene. Okay, so you can do alkylations with alkenes as reagents as well. And then you can use alcohols. So you can treat an alcohol again with sulfuric or phosphoric acid. And again, this is going to do what? Right? Cause, again, this, right, is going to take the electrons, right, forming the carbocation, right? And then the carbocation is the electrophile. So when you add an acid, what's that going to do? Protonate, right? This becomes water. Right? So makes sense, hopefully, when you think about what's going on. Okay, but I just want to return to this one more time. So this energy diagram, right? So we want to talk a little bit more about this, right? The difference between these two products, okay? The di substitution versus the mono substitution. And it also matters if you're using bromine versus chlorine. Okay, so this is bromination with bromine. Okay, but it matters if you're doing it with chlorine. Okay, and what matters also, so what I, go back here. So I mentioned that, right, the addition of 2, which would give you this product, is not favorable. But the other thing that you have to take into consideration is that you already have a bromine. So remember that Fidel's-Craft, right? The Y, right? The Y here is bromine, right? Bromine is electron withdrawing, right? That's a problem too. Would you agree? Right. And so that leads us to the next slide here. Okay, so depending on what you have as the substitution, right? For instance, bromine is right here, chlorine, right? Okay, you're going to have an effect on where the substitution is going to happen. Is it going to be right next to ortho? Is it going to be meta? Or is it going to be para? Right? Those are your choices. And so there's a direction to this substitution where the product, right, is going to form. Does that make sense? So if you already have bromine, what kind of products are you going to get? Right? You're going to get ortho, 37%. Right, but mostly para. Does that make sense? Very little meta, 1%. I mean, that's, you know, negligible. You don't even have to think about that. So you're going to get ortho-para as products, right? So if this was now methyl, what would you get?
You mostly get orthos.
Right, so ortho is more, right? But you get a good bit of para as well. Okay, and again, very little meta. Does that make sense? But if you make that one of these here, so let's say it's a carboxylic acid group, now what do you get? So again, if this is right, now you get 80% meta. Right? So what is the difference between these and these? That's really the key, I think, to remember. Because, I mean, this is like you can memorize this all day too.
The
But
size of their...
not just size, but there's a big thing here. Conjugation. Right? These are all single bonds, right? In these groups. Here I have a double bond O. Here I have a triple bond, CN, right? And double bond O. So really the meta directors are conjugated systems, have double or triple bonds. Does that make sense? So that's an easy thing. Like again, you can memorize all these groups. Be my guest. I'm not telling you not to, but you can actually, you know, kind of get some trends that you can use and you don't have to memorize all of them. So yeah.
That's why the benzoic acid that we used added the nitro group in the meta position.
Exactly, because it was conjugated as a starting material, was substituted with a conjugated group. Yep. Right, makes sense now, all coming together. We're a little bit out of order this semester, so. Right, that's exactly why. Okay, so orientation is something, right? So where does it go? And usually it goes either ortho-para, so sometimes a little bit more ortho, a little bit more para, but they usually go together. When you get para, you get ortho at a significant amount, okay? But the other choice is meta. So it's either ortho-para or meta directing, okay? So again, the conjugated systems are going to be meta directors. Okay, most of the others are going to be ortho-para directors. And the other thing is rate. And so remember, rate is, right, the speed at which you're going to make your product. So some groups are going to make the rate go up, activating, right? Some are going to make it harder to do the reaction, slow the rate down, and they're deactivating. So some of these groups are activators and some are deactivating. So you want to consider these two things. Where are they being put, and whether you're making the rate faster or slower. So there's two things here. So let's look at OCH3, right? So this is going to be a methoxy group. So a methoxy group, right, is going to be ortho-para directing. And so if you combine it with a nitration, and this could be with any, right? This could be halogenation, nitration, sulfonation. I mean, any of the electrophiles would work the same way, okay? We're just using nitration as an example. All right, so just because I don't know how to say the name of that compound, I decided to make it harder on myself. But nitric acid, I say it right? Nitric. Ah! Okay. Anyways, the point here isn't that I just keep incorrectly saying the name, but where we put that nitro group. So again, ortho-para, right? Because this is going to be, right, not conjugated. But if you, again, use the carboxyl group Okay, that's conjugated, so you're now going to get most of your product at the meta position. Okay, so again, just showing you that. Now, activation, you do kind of have to memorize this. It's not, a very easy way to remember, but most of the meta are deactivators. See, moderately or strongly deactivating. Okay, and you can really think about this, right, in a way that you're moving all of these double bonds, right, away from the benzene ring when you have a conjugated system. So you can think about that as, again, not having the double bond available to make your, the reaction happen as a electrophilic aromatic substitution. But in the orthopara, you have strong activating, moderately activating, weakly activating, and then weakly deactivating. So again, it's one of those things, okay, you just have to remember these. But you notice that the nitrogens, right, the oxygens, right, single bonded here, they're all activators, okay, and they're all electron withdrawing. All right, now what about the moderately? I still have nitrogen, but now I have a nitrogen next to a conjugated system, so I'm kind of sharing these electrons, aren't I? So it's pulling away from the lone pair, right? All of these have lone pairs. Okay, when we talk about an amide, that lone pair isn't really available for bonding. Does that make sense? So that's why these are moderately activating. And then weakly activating are the carbon chains, either a benzene or just an alkyl chain. And then the deactivators are the halogens, weakly deactivating. Okay, so, but the meta directors are all deactivated. So what does that mean? Which one is going to happen faster? Which reactions? Right? The orthopara are going to be much faster reactions than the metas. That's kind of the take home here. Does that make sense? What I'm kind of getting at with this information? I mean, ultimately you got to know all this, but you just got to kind of figure out, some trends that you can use. But ultimately, you're going to be given, a benzene ring with one of these groups attached, and you've got to figure out, is the reaction going to be fast? And where is the product, right? Where's that direction going to be? Is it going to be orthopara or is it going to be meta? Does that make sense? That's a big thing about this chapter, okay? So again, alkyl and phenol, right? These are going to have unshared pair of electrons. Again, just giving you some ideas here. Okay, so those are orthopara, but they, right, tend to be weakly activating. But all the other, right, the deactivators are meta directors. Most of the orthopara will be faster reactions, okay, except for the halogens. Those are the only ones. So again, this is just a little summary of the table, okay, to kind of help you put this information together. All right, and so with this, right, order matters. Okay, why? Why do you think order would matter? Because what's the easiest reaction when I have what? Just benzene, right, by itself. Because then I have nothing to get, right, deactivating, activating. I don't have to think about which direction. It just gets put somewhere in the ring, right? Okay, but most of the time I don't have that, right? I'm going to start with something that's substituted. And then I have to figure out, okay, if my product, right, if I want it to be para, I better start with a para activator, right? If I want my product to be meta, I better start with a meta activator. Right? So the order of my steps matter, because if this is my starting material, right, and I want to make meta, is it possible? This is an orthopara activator, so I really can't just do the nitration reaction right off the bat, right? I have to convert this to a meta director, which I can do, right, converting it to the carboxylic. Does that make sense? So I couldn't just do the nitration right off the bat. Does that make sense? Okay, but if I want para, right, you could say, yeah, I could do that first, but usually you're going to get mostly, right, so you get the nitration here, okay? But notice that in my product, I want the alcohol, right, the acid, so you're going to have to tack in the oxidation. So you can do the nitration first, right? But that's not in my product, right? So I have to convert it, but I have reagents to do that, right? My Jones reagent. So the order of the steps are important. Does that make sense? So you want to consider that. You might know, yes, I got to do this and I got to do that, but the order of, which way, in which order you do them really matters for the EAS reactions. So this is this slide here. And of course, this is, right, you got, when you're thinking about rate, you're really thinking about the slowest step. And what's the slowest step? The slowest step is, you have the electrophile, right, and it's getting the benzene to share its double bond, right, creating the carbocation. That's the slowest step. So when you're thinking about that, again, that's why I keep talking about, right, if this is tied up, right, that double bond is tied up, it won't happen, right? There won't be a double bond here. Does that make sense? Because this is the hard thing, is getting this to react, right? That's the slow step. So anytime we're talking about rate, we are talking about, right, forming, right, doing that attack to form the carbocation. So what's really important but the stabilization of the cation, right? Which already, again, a theme for the whole course. The more stable the cation intermediate, guess what? The faster the rate is going to be, right? So if we look at some of the activating groups, when we go over here, so why would having this next to a cation help? Right? This is a strongly activating, so we are saying this is going to help the rate, right? How is that going to help the rate?
It's not going to try to pull any,
right? Because
or give off any.
This is already like this, right?
Yeah.
Unhappy, right? So if I have something over here with electrons, guess what's going to be able to happen?
Shift.
It's going to be able to shift and share, right? Does that make sense? So again, when you're thinking about these things, if you can understand what's going on behind the scenes, right? It might make more sense than just blindly memorizing. I mean, ultimately, yes, you have to know all those groups, but if you can understand what's going on, it's really the stability of your cation that you're concerned with, because that's the rate limiting step. That's what this slide is telling you. So for the ortho pair, the ones that are activators, right, they're going to make the rate faster. They're going to help to make the cation more stable, right, at the ortho and para position. Does that make sense? So for the meta, now the cation is going to be less stable at the ortho or para because they're deactivators. Okay?
So would an OH work there, just like NH2?
An OH is the same. It's also, if you go back here, right, OH is there too.
Okay.
Yep. So
How
it
would
does the same.
OR work?
OR has the electron pairs on the oxygen as well. You don't need the H. You can have an H or an R. Okay. So that's what this is saying. So this leads us to this then, right? Because we're looking at when the carbocation is present, right? That's going to be the slow step, getting to this point. So we're trying to see, okay, if we move things around, right, where is the most stable? Does that make sense? And so for this, right, here's the meta position. None of these are really great. See, they're not really, great here. But in the para position, this one is the best. Why is this the best? It's that double bond where? Right, the charge on the oxygen, right? See how none of these, the charge never reaches the oxygen. That's a problem, right? Because the best place for the charge to be is not on carbon, right? But on the oxygen. And that's why you get mostly para for the OCH3, the methoxy group. Does that make sense? So what about for the nitro group? So this is a meta attack. So again, if we look at the meta, okay, these are the ortho-para positions. None of them really get you a better one, right? But you have this here, okay? I'm sorry, I went backwards on that one. So these are the meta up here, right? So this is going to show you, okay, they're all the same. But this one is particularly, okay, bad. Why? This would be the para, right? But why would this be really bad?
Because
This
there's-
favorable.
The
The carbocation next to the conjugated, like that's a big hole right there, right? Because you have those electrons here, and we're trying to get, right? That is pulling it away from, right? We're trying to get the electrons in, and the conjugated system is pulling it out. So that's why meta at the top, they're all equal, right? But on the bottom, you can see you get that really unfavorable at the para position. So this is just, again, summarizing this information. So this resonance effect that we're looking at, right, moving the double bonds around, really is a way of stabilizing your cation. That's what we're trying to do. So when you delocalize the positive charge, it lowers the activation energy, which means the group is going to activate, make the rate go faster, right? Because you want to make sure, right, this bond, this positive gets to, right, a good place. That's delocalizing the positive charge. That's what that statement is telling you. So when you can do that in a, right, productive way, then it lowers the activation energy, which makes the rate go up, right? Because the activation energy going down makes the reaction go faster. Okay? But of course, if you decrease the electron density, it deactivates, right? Why is that? Because again, I need to be drawing electrons in, not out. I'm already missing electrons with that positive charge where it is, right? So if you decrease the electron density, you are deactivating, making the rate go down. Making the rate, right? Gonna slow down the rate, I think, going down. Not the right way to put it, but making the rate, right, slower. And I put blue activating, red deactivating. I know it's not printed on yours like that, but hopefully it kind of differentiates the two statements. Does this make sense? So again, it's what we're talking about, stabilizing that cation intermediate. So that's how the activate and deactivate works. Now that's with the resonance. Now what about with the inductive effects? So the inductive effects, if you can release electrons, again, electrons towards, you're going to activate, right, electrons towards the cation. Okay, if you're pulling electrons away, right, decreasing, making it even more positive, you're going to deactivate, slow the rate. So I kind of try to summarize here. This very not so well-written sentence, but delocalizing the positive charge, right, and releasing the electron density is good. Does that make sense? So delocalizing, making sure the double bond, right, goes around your ring and ends up in a more productive place is good, right? And giving more electrons to the cation, right, that's going to be good. But taking electrons away is going to be bad, right? I don't know if I can make it any more simple than this. And no, I mean, you need to kind of think it through, but, all right? Because again, ultimately, this has to be as stable as possible. Does that make sense? So that's what we're trying to do. Okay, that take home, I mean, it does need you to think this through, but. So this is just showing you the halogen is the only orthopara director that is deactivating. It's weakly deactivating. And this is just showing you why. Okay, because again, right, it's showing you that you're going to get that, right, the shift here so that you can take the the electrophile, right? So this is again your cation, right? And so the cation forms here a double bond and it puts the positive charge on the more electronegative atom, right? So it makes sense that this is the para position, right? But why would this be deactivating? Why would this be deactivating? Right? This is showing you why it's para, but why would it be deactivating? What's the problem? What's bad about this? Right? That this is electron withdrawing, right? Which is the bad. It's taking away electron density. So even though the para is the right position, unfortunately chlorine, right, fluorine, bromine, the halogens tend to remove the electron density from your benzene ring. That's what this will show, because it's the only ortho pair that is deactivating.
Would the no bond on the chloride be stable?
It is, that's what I mean. So this is good as far as the stability, but it does slow down the rate a bit because the chlorine is also doing something bad. It's doing something good, but also something bad. That's why it's weakly deactivating and not, strongly or, really bad. It's kind of good bad. So, but yeah, the double bond there is a good thing. So, and you can also do a nucleophilic aromatic substitution. So all this chapter has been EAS, right, electrophilic, but you can do NAS, nucleophilic aromatic substitution as well. And these don't undergo the traditional SN1, SN2 that we see for nucleophilic substitutions. Excuse me, but you can use nucleophiles, okay, to do the substitution at the aliphatic substitution, so that means a carbon chain. Okay, so these can happen, but they're far less common, so we really don't talk about it in this class very much at all. Okay, there's just a little blurb at the end of chapter 22 about it.